Hello OpenFoamers, welcome back to our discussion. Okay, so in the last video we're talking about chtMultiRegionFoam, and what I have done over between the last video and this video is basically to run this utilities for 1000 seconds so that the sphere actually cools down. Alright, so originally there was 10 seconds of data. I just simply changed the control dictionary to run for 1000 seconds at about 5-second intervals. Well, it was originally like 2 seconds from I think like 12 seconds, 14 seconds, 16 seconds, 18 seconds, and then after I think 20 or 30 seconds, I just made the data recording interval to be 5 seconds a piece. Now, of course, all of these contains the data points for every single little part of the mesh. So technically speaking, that's not needed. We can use this. We can use this simple thing in control dictionary called perch right. In this, I just highlight this for you here, perch right. So remember, if we key in a number there, for example 6, it will keep the latest 6 time steps and delete everything else. And the only thing you kind of want to use to compare are these functions, for example the wall heat flux, the heat transfer coefficient, and of course the area average, which records the surface temperature of the sphere over here, because we use this thing called surface field value, and of course the heat transfer coefficient, which we spent a fair bit of time discussing, whether it was the correct heat transfer coefficient and the correct reference temperatures that we were using to measure it. So okay, so first thing first, I want to take a look at the data. I want to take a look at the data, and the data is as such. You go to the post-processing, okay, and we go to oil, and we take a look at wall heat flux, right? So there'll be one part in the 0 directory and one part in the 10 directory. Now what does this mean? 0 means that you start executing your functions at time equals 0, and when I continued after 10 seconds, the simulation started at 10 seconds, of course, and then we had another re-execution of the functions, for example wall heat flux. So from 0 to 10 seconds, we have the start time of 0. We will have this wall heat flux dot data. Okay, so I will have all of this data down. Alright, and it will have the max x, min x, max y, min y, etc. And of course our all important oil to sphere boundary, where we will have our integral heat flux. This is actually equals to, hold on, let me open up Microsoft Word. See, hold on. Alright, so I've opened a Microsoft Word, and what we were trying to calculate is, of course, this we are trying to get this integral data out. Okay, so what is this? This is actually equals to the heat flux times the area. Alright, so this is what we were actually calculating in this integral over here. So this is QA, and this will be accordingly equals to HA T fluid minus T solid. So this is how we find the H. If you want to calculate heat transfer coefficient, we just integrate Q dA, and you divide it by the area. You divide it by the area, and accordingly the fluid temperature and the solid temperature. We use it to normalize to get this heat transfer coefficient. Okay, so that's what we do. So for the first let's see, where is the Ubuntu? For the first 10 seconds, data comes in every 0.5 seconds. So normally we want to copy and paste. We want to select all the data here, but you see, using the VI editor, it's a little hard to do that. Now the alternative solution is to use Notepad to open this up. So when you see this surface view value.data, okay, you navigate to your Ubuntu folder. Not going to go through how to do that again. You navigate to your Ubuntu folder. We go to wall heat flux, and then we start at 0. We're going to look for wall heat flux.data. We open with Notepad. So open the data file with Notepad, and you will see this. And you just select all, Control A, copy and paste, and you put it in Excel. So I'll just demonstrate for you one time. Copy and paste here, and then you put it in Excel. And accordingly, every piece of data will be put into nice rows and columns for you already, at least in my computer. So that's okay. And likewise, you can do the same. You can do the same for the one going from 10 seconds all the way to 1000 seconds. So this is the function that started measuring at 10 seconds of simulation time. You go to wall heat flux data. Again, open it using Notepad. Open it using Notepad. And just select all, copy and paste. See? Select all, copy and paste. You should be able to get all your data. So what I've done in the heat flux data, part 1. Alright. So scroll to the right here. Is I basically pasted all this data over here. Just ignore what I have to the left. Ignore what I have to the right. Okay. Ignore what I have column G onwards. I'll just zoom in on here. So I've pasted everything here, right? All the pieces of data from 0.2 seconds all the way up to 1000 seconds. Sure, good. Now how do we plot a graph? Or at least get rid of this max x, min y, etc. So the thing to do is you go to view, and we use this filter kind of a thing. Okay. Or data, and we go to filter. Alright. So go to the data tab in your Excel. Press this thing called filter, and we go to selecting only oil to sphere. Alright. That will give you only the oil to sphere data points. So just copy all of this, paste, and then you will see that, oh yeah, we only have the oil to sphere data points that are there. You can see what I'm highlighting here. It's only the oil to sphere data, and everything else is neglected. So this is how we actually get use Excel to filter out all the unwanted data points and just get the oil to sphere data points. So I have already done that when I pasted it. Okay, so everything I have is here in a wall heat flux. So this is the column where I have this wall heat flux over here. These two columns, again, this the max and the minimum wall heat flux data, I kind of just took it out. I just went for the integral data, which is this integrate QDA. And now, of course, the next step is to find the surface temperature. And where do we find the surface temperature? We just simply go to our, what do you call that? We go to the solid surface temperature by going to this area average we were talking about before. And we go to, again, 0. And we go to surface field value.data. And then we'll see the average surface temperature integrated by area. And of course, the OpenFoam in-house heat transfer coefficient function. So, okay, what I did is I went to go and copy and paste out all this, the surface temperature, again using our trusty little notepad. And we go to area average. We go to both the 0 and 10. I just went to copy and paste all of this data into Excel. So that's what happened. That's what happened in this these two columns here. I pasted all the temperature and heat transfer coefficient data over there, and what I just wanted was this average temperature data, which I went to copy and paste, and I put it in this column here. Then how does one calculate the heat transfer coefficient? Heat transfer coefficient is fairly straightforward. As you look at the Word document, we just take the integral, divide by the area, and of course TF minus TS. Well, I mean TS minus TF, sorry. TS minus TF. Alright, it should be, yeah, one of those. It's just basically temperature difference. Hold on. Okay, according to Wikipedia, you should have the temperature of the surrounding fluid minus the temperature of the solid. Okay, so temperature of the surrounding fluid minus temperature of the solid. That's how we get the TF minus TS. So, okay, I kind of mixed it up there. But what I did, okay, I put the temperature of the fluid here, 300 Kelvin. Okay, 300 Kelvin. And this is the solid surface temperature, which is 499 and is decreasing all the way. Sure. And the area here is 4 pi r squared. 4 times pi times r, which is 1.5 cm. It's a 3 cm diameter pebble or 3 cm diameter sphere. And then I convert it into meter square by dividing by 100. And then I put the power 2 here. And that will be the area of the pebble. Now if I want to calculate the heat transfer coefficient, again very simple. I take the wall heat flux integrated divided by the area. So I put F4 to actually lock the cell. Then I put TF minus TS. Again, for TF I need to lock using F4, and I'll close both brackets, and then I'll get a negative heat transfer coefficient number. Of course, that's because the heat flux here is kind of it's a positive. The sign convention kind of changes. So of course, heat transfer coefficient should always be a positive number. What I can simply do is just put a negative sign in front to just do the sign change to make it more like presentable on the graph. And then, yeah, I will have this positive heat transfer coefficient. And what I can do is just copy and paste this down and paste it here. Okay. Normally if we just plug and play the formula, we'll get a negative, but I just convert all of this into positive data and I pasted it here. Alright, this column here. So I have this column called H, wall heat flux method. I pasted the values there, and of course I compared to the area average. Okay, so the area average heat transfer coefficient, which we use OpenFoam in-house method to do and calculate, it was over here. Can you see this column here, which is what we pasted from our notepad. Okay, surface field value, wall heat flux, I'll get it out. Okay, yeah. So this is what we copy and paste from the notepad, and this is what I do here. Copy and paste the area average heat transfer coefficient, and I just convert all of this into positive numbers, and then we can plot. So what I do is just Control Shift and right arrow and down arrow, and then I'll just put a scatter plot. Okay, so I select the negative numbers. So the area average heat transfer coefficient, which is negative, I just delete this because it's kind of redundant. This H, I want to plot it on a secondary axis, so I go to this bar chart looking thing on the series options, put in secondary axis, and likewise for this, which is a secondary axis. So this is what the chart looks like, and then if I change the title to temperature and heat transfer coefficient versus time, I will get this following graph here. Now you can see there's a slight discrepancy between the area average heat transfer coefficient and the wall heat flux method, where we use the 4 pi r square area. But you can see the trend is more or less the same. And if we just do a division, like the area average over the wall heat flux, and then we just pull it down, we can see it's more or less just the same factor of difference, 1.0129. This is because I think when you use the area integration, for, let's say, for the sphere, right? For the sphere, you have the area integration. Yeah, this is a sphere. When you have this area integration, it's actually the discretized area, meaning to say that it's not really a perfect sphere, but it's a lot of flat surfaces which approximates a sphere. So that actually explains the discrepancy between the wall heat flux method, which we were using just now. I used the word to do it, and then of course the area average heat transfer coefficient offered by OpenFoam. Of course, the area average heat transfer coefficient by OpenFoam, that's probably a faster method. Then you don't have to do it manually. But it's always good to double check whether we are measuring the right heat transfer coefficient by using this wall heat flux method, the function, to see whether we are measuring the correct heat transfer coefficient. And indeed, we are measuring the correct heat transfer coefficient within the certain error that's afforded by, that is probably due to the difference between the surface area of a perfect sphere as compared to the surface area of a lot of flat surfaces which approximates a sphere. Now, so far so good. You see this trend of exponentially decreasing temperature, and of course the heat transfer coefficient kind of doing this wavy thing. Alright, the heat transfer coefficient is kind of doing this wavy thing with respect to time. Of course, we cannot expect the heat transfer coefficient to be constant with time. And why is that? Because the sphere is kind of cooling off, and as the sphere cools off, there are some things that will start to change. For example, the Grashof number, and therefore the Rayleigh number will change. You can see that this is actually a temperature dependent kind of a thing. The temperature difference, okay, Rayleigh number is quite dependent on the temperature difference between the solid and the temperature of the fluid, and therefore when the Rayleigh number change, and of course the Prandtl number of the fluid kind of changes a little bit. Prandtl number doesn't quite change because the bulk fluid Prandtl number is the same, but the local Prandtl number changes. Now of course the Prandtl number we'll probably use here is the bulk fluid Prandtl number. Okay, the bulk fluid Prandtl number doesn't change, but the Rayleigh number will change. And if the Rayleigh number changes, the Nusselt number will change according to this correlation over here. You can see this Nusselt number equals to 0.589 Rayleigh number divided by some function of the Prandtl number. So that if the Rayleigh number changes due to the temperature changes, Nusselt number will change, and therefore Nusselt number is a non-dimensional heat transfer coefficient that will change as well. So as the temperature of the surface change, we expect the heat transfer coefficient to change. Now, question is, of course, will all these data actually fall within the correlation that is being put here, as we have a plot between the Nusselt number and the Prandtl number. So that's a very important question for us to answer, to see whether all our data actually fits into this simulation. And of course, we need to test if our setup is actually what do you call that? Is it a turbulent or laminar flow? And we have explored that before. I think below a certain Rayleigh number, it is actually a laminar flow. So yeah, actually from this paper, the fluid flow and heat transfer of high Rayleigh number natural convection around heated sphere, the critical Rayleigh number is 3 times 10 to the power of 8. So we'll need to calculate the Rayleigh number later on, using all the data, the thermophysical data that we do. Of course, we'll cover that probably in the next video. But this is just to show the heat transfer coefficient versus time. So okay, I'll just make the axis a little nicer. Maybe I put from 300, and this I will put it at the number 4. Start at about 40, and then yeah, this is what the graph of it should look like. So this corresponds to this, and the temperature corresponds to the left. So thanks for watching. I'll see you guys in the next video. I just copy and paste this into here. Probably I want to upload all of this into GitHub. Yeah, at least all this data is very important data into GitHub. So hold on, let me copy and paste. Okay, so yep, thanks for watching. I'll see you guys next time. Goodbye.